That's the scary thing. That's the quantum apocalypse.
Yeah.
Everything we think of as safe right now, in maybe 10 years or so, it won't be.
I didn't know that we were going super deep into quantum physics. I mean, honestly, I wasn't expecting that direction. But
that was
that's interesting nonetheless.
You know that was my background before I got into computers, right?
I know. That's why I kind of let you talk, because it's definitely not my background. I mean, I know quantum physics because I read like a Neil deGrasse Tyson book a year ago.
Right.
You know? I mean, like, 100% honest with you, I'm not 100% smart on the math front. I'm not there 100%. But what I do understand is that if you take the current algorithms that we're using now, those can be easily broken. So we have to come up with something that is exponentially harder to crack. Welcome back to another episode of the Cyber Guys podcast, the cybersecurity podcast for everybody. My name is Andrew Valencia, and as always, I'm joined by Mike Hill. And are quantum computers going to bring about the cryptopocalypse? We're going to talk about that today. But first, take a second to hit that subscribe button if you're not already subscribed. That way, you'll never miss out on any of the new content that we're publishing every single week. If you're listening to us on any of the major podcasting platforms, make sure you come visit us on our YouTube channel at www.youtube.com/@CyberGuysPod, all one word. We post videos regularly, including weekly tech talks that Mike puts out every single Friday. Make sure you drop us a like, share us with a friend. And now let's talk about quantum computing and the coming cryptopocalypse.
Yeah, really, before we even get into that, we kind of need to just back up, because crypto is based on numbers, and our numbers are based on binary. But when we get into quantums and qubits, we're talking about a whole nother paradigm. So first, let's just talk about, okay, what's quantum mechanics all about? And the short answer is it's a field of physics that tries to look at the fundamental elements of the universe, subatomic particles, atoms, the behavior of energy transformations in a term that can be measured and understood. In fact, that's really what the word quantum has reference to. I mean, it comes from the word quanta, which means how much. In other words, when we boil down an element of energy into the most finite quantifiable measure, that's a quantum or a quanta. Like a photon is a quanta for light. Now, when we start analyzing and looking at energy and energy transformations and conversions in this way, what we come to and what we understand is there are certain principles that kind of behave differently than classical physics would have us believe. So we see the subatomic world as distinct from the material world that we all exist in. So ultimately, quantum mechanics is a field of study of how that world works. And it's one of those cool terms. I know back when I was a young physics student, I wanted to be a specialist in quantum mechanics just because it sounded cool. And it is cool. Here's some of the core principles that get into how we examine quantum mechanics, and then we'll get to how that fits into quantum computing. First, we have this principle of wave-particle duality. When we look at quanta, we don't see behavior that's exactly like a wave, but sometimes that's the best way to measure the behavior. For instance, we measure electromagnetic radiation in terms of wavelengths. So we think of it along the wave theory. At other times, we think of it in terms of like little packets of energy that behave almost like particles. Even though they have no mass, they have characteristics that can be quantified and analyzed and studied as if they were particles. The thing is, with modern quantum mechanics, we realize that neither one of these states is actually accurate. So that's what we call the wave-particle duality. Another concept in quantum mechanics is the idea of superposition. And this is one of the ones that makes quantum computing so fantastic. Basically, with superposition, what we basically mean is this. A quanta could seemingly appear to have different positions in the same time. One way that some like to describe it is kind of like identifying the location of intersecting ripples on the surface of a pond. It's almost as if it's having two different behaviors simultaneously. And that characteristics of quantum leads kind of to another principle, what we call the uncertainty principle. This is one of those principles that was established by a scientist named Heisenberg. And if you ever watch Star Trek, you may have heard them talk about the Heisenberg compensators. Well, what that's really about is the fact that we can never identify both the speed and location of quanta at the same time. If we can measure the speed, we can't measure the location. If we can identify the location, we can't identify the speed. So you can never actually ever know exactly where any packet of energy is at any given time. Which is why, even though it's fun to watch the transporter beams beam you up or beam you down, technically that's based on our current understanding of quantum mechanics, impossible. But nevertheless, that's one of our principles. Another one is quantum entanglement. This is one that the movie Quantumania liked to play around with. Actually, I think it was the second Ant-Man movie that played around with this concept. And this is the concept that two quanta can actually be entangled and be part of the same system, having an effect on each other, irrespective of the proximity to each other. So the idea that you could literally have two entangled quanta separated by light years, and yet, because they're part of the same system, existing in some other state of reality that we really can't fully understand yet, they can affect one another. It's the combination of entanglement and superposition that gives us the ability to do some really, really fantastical things in quantum computing. Instead of using base 2 numbers, which are fixed, finite, what they are is what they are, instead of using what we call bits, we use quantum bits or qubits. And because of the superposition principle, they can hold different values and be used to define complex states beyond just the simple on and off state that we get with binary.
Wait a second, Mike. Let's not just breeze over that real quick. Okay, so currently, today, right? Computers think in ones and zeros. We talk about, we use the terminology of binary, right? We have ones and zeros.
Which is the foundation of all Boolean logic. Is it true or is it false?
The foundation of all Boolean logic.
Yeah.
Absolutely, right? So we have 0, 0, 0, 1, 1, 0, and 1, 1, right? And all the combinations thereof. But what you're saying is with qubits, we have, they're all of that and the same at the same time?
They can be all of that at the same time and many more. So the idea of dealing with simple number systems as a way of encoding a qubit, it's potentially infinitely more complex than that. And at the very least, even to the extent that we've theorized and used it, even if you can hold multiple states within the same qubit, the idea that you use that for a basis in logic or a way of defining something that would be encoded as a value, you create exponentially more values at the same time. So yes,
because a qubit can be 1 and 0 at the exact same time.
Correct.
Right.
That's the idea of superposition. But ultimately, because of that variability, you can create forms of state, or you can create ways of representing state that is beyond what you could represent in a similar bit space. So ultimately, we're taking the way we do the math behind the logic in computing, and we're ratcheting it up, to exponential levels. I mean, it's kind of like what we did with dense wave division multiplexing. In extremely high speed optical networks, fiber optic networks, we transmit binary data with pulses of a laser, right? But here's the thing. With lasers, we're transmitting light. With light, we have different wavelengths, which means theoretically you can transmit different signals on different wavelengths simultaneously. So even if the actual basic throughput of a given transmission medium, fiber optic cable, let's say you're maxed out at, let's say a gigabit. If you're running on 100 different channels at the same time, you're multiplying that speed for each channel that you have to transmit at the same time. So, you're getting 100 times the throughput, the maximum throughput of the medium. That creates an opportunity for, exponentially more information to be transmitted at the exact same time. It's kind of like that. Even that's more linear than the relationship between bits and qubits. But it's kind of, in a way of just kind of getting our heads around what we're doing in terms of jumping up within the same signal, within the same system, exponentially larger values, therefore substantially greater amounts of information. Now, here's the area where it gets really interesting when we throw in the principle of entanglement. See, now we could have qubits that are part of the same system, perhaps encoded into some sort of cryptographic system. Then we can actually build with quantum cryptography systems where you don't have to actually even have a key exchange. You simply only have to entangle the keys on the counterpart systems, and wherever they are in the world, your key can open and close your crypto encrypted mechanism, which creates a very, very strong basis of authentication without having to worry about ever compromising key exchanges or the sort of things we do now. So all that is just kind of some of the goofy fun stuff about quantum computing. There's a lot more, but those are some of the fundamentals. But here's the thing. With Moore's law, right, every so often computing power doubles. One of the reasons why we keep making longer passwords and we keep, worrying about cryptanalysis being more powerful as the computers get more powerful and therefore needing stronger crypto. I mean, some of the older crypto systems, for instance, there's nothing really wrong with the design of some of those old crypto systems. It just so happens, though, that our computers have gotten so powerful that what would have been a work factor that no one could reasonably reach to break a code, now with the computers being so much more powerful, the work factor is a lot less than what it used to be, and therefore we have to obsolesce those older crypto systems. Well, with the quantum leap, quantum leap forward in quantum computing, the mathematical systems in which all these things are based, becomes elementary arithmetic. Something that seemed like it was going to be unbreakable, now with the multiple states that we can maintain with a qubit-based system, can be completely broken. It's all obsolete like that. That's why.
Like right now, right? Well, because right now, right, with binary computers, like my 16-character password that has special characters, upper lowercase letters, takes something like 80 million years to break. But with quantum computing, that can be broken like this. That's
the idea. Dramatically more powerful computers. And that's why some people out there are concerned about the crypto-apocalypse, which brings us back really to the topic of the day. What is this crypto-apocalypse? It's the idea that all of our systems that we're using to make us feel safe are suddenly going to be obsolete. I mean, here's a way to think of it.
Well, and imagine, but it's not even that they're obsolete. People, hacking groups are planning for their obsolescence, right? There's a lot of awareness of quantum computing and what's going to happen in the next decade to 2 decades. And that's why you have hacking groups that are conducting what do they call store now or harvest now and decrypt later campaigns, where they're just sucking in a ton of information and they don't need to worry about decrypting any of it because they know they're going to have access to something that at the quantum level to break all of the encryption within the next decade. Yeah. And that's the scary thing.
That's the quantum apocalypse. Everything we think of as safe right now, in maybe 10 years or so, it won't be. It won't be, buddy. Look at this article I guess we'll put it up for everyone to see. But talking about the crypto apocalypse, it appeared in Security Weeks. Look at what it said. It says the waiting time for general purpose quantum computing is still probably decades away. The arrival of crypto-analytically relevant quantum computers, or CROCs, that will herald the cryptopocalypse, will be much sooner, possibly less than a decade. So just like you said, just a decade away. At that point, our existing PKI protected data will become accessible as plain text to anybody. And the harvest now, decrypt later process will be complete.
Yeah, well, so I think that's important. That's an important point. We're not just throwing up. This isn't just a scare tactic or catastrophizing unnecessarily, right? We have means of encrypting right now that, specifically asymmetric cryptography, where yes, your public key that's out there that's supposed to be used to encrypt data can be completely de-encrypted extremely quickly within the next decade. How many applications, how many websites do we currently use that same type of cryptography that in 10 to 20 years is going to be completely broken? That's the scary part. So we have to completely reevaluate how we encrypt our data.
Yeah, exactly. I mean, and that's why we're hoping that some viable, potentially commercially viable quantum cryptography will be on the table before, quantum cryptanalysis gets ahead of the game.
Right.
Part of the question is, the stuff that they're harvesting, it's certainly sensitive now. Will it still be sensitive by the time it can be breached? If that's the case, then it's really going to cause people a little bit of pause and chagrin over the information that they convey in transit across conventional communication pathways. It's definitely causing a lot of heartburn. This is what it says going on. It's important to note that all PKI encrypted data that has already been harvested by adversaries is already lost. We can do nothing about the past. We can only attempt to protect the future. And that's kind of like what you're saying. Everything travels across the same internet, and anyone can sniff anything on the internet. The only protection is the strength of the crypto and whatever was collected in transit. But if you've communicated across the internet and it's been harvested and someone has stored it, even though it's encrypted, it's stored on a box that they're going to hold on to for who knows how long, with the hope of one day applying a quantum computer against it to figure out what it is. Anything like that is lost.
That's why NIST, the National Institute of Standards and Technology, right? They even put out a competition for people to come up with encryption techniques post quantum computing, right? How to actually encrypt data against the abilities of quantum computing. And there's a few different ways to do that. But one of the ones that they had, I think back in February, I'm going to find the article, but back in February, it was broken. It was actually broken already. I think it was called Crystal's Kyber, was already broken before
even getting quantum.
The full extent of quantum computing has even been realized. We have quantum computers today, but they're nowhere near the magnitudes that we're going to see in the next 10 to 20 years.
And really, the quantum computers that exist now are prototypical. They're just playing around with one aspect of the potential. Like, for instance, some will just work on the concept of superposition and how that can actually be applied in practical computing and computer science, ways of establishing programmatic behavior or artificial intelligence, that sort of thing. In other words, how do we actually program with qubits? We have to actually come up with a set of principles on that. Right now with quantum computing, there is no standardization. There is no printable. It's just conceptual okay, if we have the concept of superposition, if we have the concept of entanglement, how do we turn that into practical applications that we can then apply to the way we store and process information? That's all amorphous and undefined yet. So although these systems exist, they're nothing compared to what they will be, in the coming decades.
And I don't want not to hype on the coming not to hype on the cryptopocalypse that is going to be coming, the cryptopocalypse, but there's an entirely new field that's out there, newer field anyways, that exacerbates a lot of the concerns that we have regarding quantum computing, and that's AI, right? AI functionality with a quantum computing background is kind of scary, right? Because even the NIST, recommended encryption technique that they put out there was broken by AI. I'll put the link up to the article when I get it. I'll put it up there on the screen right now. Boom. There it is. But yeah, it was like an AI deep learning side channel attack that broke it. So that's even before we get into the quantum computing being utilized as a resource to break some of these encryptions. That's something else that entirely. I think we could do a whole other episode on AI assisted quantum computing.
Yeah.
Whoa, that's a whole different story.
AI is a threat on its own because the bottom line is, programming is a methodical behavior. Designing software is a methodical behavior. The math that we use to develop keys for encryption and decryption, it's all mathematic. And ultimately, sad to say it, a well-designed AI system does math better than humans. As I've said before, AI does not match the human brain in terms of inductive reasoning. But AI can dramatically outperform the most brilliant person in deductive reasoning. So to the extent that you're looking at it as a tool to deduce what something is when it's actually already there, the potential with AI is beyond imagination. And then you take the processing power of quantum computing, which then is exponentially beyond anything we can do with binary systems, even our most sophisticated, high-speed, multiprocessor, super sophisticated supercomputers. It's still nothing compared to what we can do with quantum computers. So you took AI that's designed to deduce at astronomical speeds with efficiency, brutal efficiency, and then you combine that with the processing power of quantum computing. And any seemingly unbreakable code today is like, reading Dr. Seuss. No, it's easier than that. It's like reading, what did I read my kid when they were little? I think of it, the simplest,
Dr. Seuss is pretty simple.
I guess Dr. Seuss, one fish, two fish, red fish, blue fish, whatever. The point is, it's like reading the most basic children's book.
Yeah.
That's what we're talking about here. Once we have well-designed AI running on top of quantum computers. So
we shot up the red flare. We know the coming cryptopocalypse is coming. So what is being done right now to safeguard our future with regards to encryption?
Well, the answer is even stronger crypto systems. Because in the end, math is still math. Numbers are still numbers. We just have to get much, 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 much bigger numbers. I mean, some would say that AES 256 is quantum safe. And maybe we may have to actually get up to even bigger key sizes than that before we can be more confident in saying that. But in the end, if the algorithm itself is sound, then we're really just talking about work factor. It's not like qubits are smarter than bits. It's not like a quantum computer is somehow different in terms of the way logic works. Logic will still work the way logic works. Math will still work the way math works. But we have to start looking at the work factor of our cryptographic solutions in terms of, okay, forget about the most powerful supercomputer today. How long would it take a supercomputer of tomorrow, based on quantum computing, to break this code? That's ultimately how we prepare for this. But everything that we're using, all the conventional, off-the-shelf, open source stuff, stuff that, frankly, NSA knows how to crack it anyway, that kind of stuff, it's going to be completely obsolete.
Yeah.
And
well, it even takes an approach where we have to kind of question the conventions of current encryption techniques, right? I was reading an article recently that talked about the future of post-quantum computing with regards to encryption is going to be like lattice encryption, where you have multiple vectors on 1,000-dimension plane that are basically where you start with a public key and a private key. And that in order for you to even begin to even break it, you have to traverse a 1,000-point or 1,000-dimension point vector system and that even quantum computing makes that is incredibly difficult for it to break that.
Yeah.
So even the way we're having to think, that's exactly my point. Think about encrypting is fundamentally changing for better, obviously, because we have to meet this need of having higher encryption standards in the next 10 to 15, 20 years.
Yeah, because that's really the point. We have to make the math harder. It doesn't. We don't have to stop doing what we're doing, but the math cannot be something that a regular computer could eventually get to. We have to start thinking exponentially more complicated.
Yeah,
and
that's the thing, because you brought up AES 256. You brought up AES 256, and it's not that it's unbreakable, but it's unbreakable within any relevant period of time that's usable, because it still takes millions and millions and millions and millions and millions of years for current computers to break that kind of encryption. But with quantum computers, it's a lot faster. So we even have to kind of rethink how we're encrypting. Even with our strongest encryption techniques, we have to completely reevaluate. And I'm being 100% honest with you, I'm not 100% smart on the math front. I'm not there 100%. But what I do understand is that if you take the current algorithms that we're using now, those can be easily broken. So we have to come up with something that is exponentially harder to crack. And there's a couple different techniques. The lattice one is one of them, but that's what we're having to do now. And I think, and there are researchers, computer scientists that are on the ground right now doing research to come up with that actual, with those techniques and those standards. I think NIST is expected to come out with that standard next year. But they may push that back again, just seeing how where things are going. But we're coming to terms with it in a real sense. So there's a problem, but we have potential solutions on the horizon.
Yeah, we are. So is it a crypto apocalypse? Yes, but
I mean,
is it really a crypto apocalypse in the absolute? And the answer is no. It's an apocalypse for today's crypto. It's the end of today's crypto. It's the end of the way we do it now. But it's not the end. It's not the end by any stretch of the imagination. It's just the end of the way we do it now. And here's the beauty of it. Just like we always talk about on this show, you have tiers of risk. As quantum computers become commercially viable and they exist, who's going to be able to afford them? A kid in his mama's basement? No. Local gang of cyber criminals?
You got to have money. You got to have that money.
No. In the beginning, it's going to be nation states that have quantum computers. large institutions, and then eventually major corporations, and then eventually they'll work their way down. As that level of computing power works its way down the tiers of society, then hopefully the information securing your systems will be working their way up, and the two will meet. The organizations that need to worry about it are national security institutions, financial institutions, the sorts of institutions that would be at the top of anyone's target list. So in other words, let's say China, which, China's having some breakthroughs right now in quantum computing. Well, if they want to hit, the servers of the U.S. government, they're going to be the top rung. They're going to be the first threat. So most importantly, the government, the organizations that are protecting national security interests and that kind of thing, they're going to be the ones that need to respond to the cryptopocalypse faster than anyone else. For the rest of us,
and they are. Let's be real,
believe me, they are.
They're dealing with it. And the NSA and CISA, they've even come out with like quantum computing resistant algorithms. They've already put that stuff out there, and we're still 10 years away. Yeah. So they're on top of it. They know what they're doing.
So there's no reason to panic about this, but it is something to be aware of, and it is something to think about in terms of long-term storage of your sensitive information. You're storing it for the future
thing too, right? Is your account number, your banking account number may change in the next 10 to 15 years. Your address, your home address may change in the next 10 to 15 years, but your social security number is definitely not going to change in the next 10 to 15 years, or in most cases, it won't change in the next 10 to 15 years. So there should be a understanding of what type of information is out there, what type of information is going to be long lasting, and what type of information is already exposed, even if it hasn't been decrypted yet, because it will be in the future.
And sadly, just as a tip, since you bring up social security numbers, always proceed as if your social security number has been compromised. You use some sort of credit monitoring tools and other thing like that, because more than likely, it already has been. More than
mine is. Yep.
Sad truth.
I can thank multiple government institutions for that.
Well, no, don't get me started on that one. But yes, exactly. So the cryptopocalypse is coming, folks. But don't worry about it. It's okay.
Here we go. All right. Well, that's where we're going to cut it for today's episode. As always, we super appreciate you guys watching these videos. Make sure you check out the YouTube channel for even more great content that we're putting out every single week. If you like this episode, make sure you drop a like, leave us a comment, and don't forget, stay safe, be secure, be sure. We'll see you next time.
Take care.